Good evening, everyone. Today we're going to be reviewing shielding through the shelter entranceway. So what we're talking about when you design shielding or a geometry shielding for a shelter, we usually use an air burst. Usually it's a 500 kiloton air burst. And you can see here that an air burst is going to give you the most radiation penetration inside the shelter. A surface burst is not as bad, but it's still pretty close. It's something that has to be dealt with. So this is where the radiation comes in. This is where the radiation comes in, and that's the shielding that we do. You can put a barrier shielding in there, and you can use the tables from the overhead radiation shielding, and you can reduce that. But if you use steel to reduce it by half, you're going to have to put 1.2 inch thick steel. It's usually not economical to put that heavy a plate of steel in these entranceways, and then you have to put it on hinges. It's pretty expensive. This is what's called a straight-in entranceway. This goes straight up, and it doesn't have a radiation bend, and depending on the geometry, it may not need a radiation bend. This one doesn't. A walk-in hatch, walk-in entranceway, is big. This is a big area, lets a lot of radiation in. This is a big entranceway, but it's long. It's on a big shelter. So this is going to be long, and you design that entranceway to reduce the radiation that comes into the shelter here. The overhead radiation is based on the distance from here up to the surface of the ground. So to determine that dose, we know the dose is outside. To determine the dose, it's based on the horizontal distance from here to the center of this entranceway, the vertical distance from this center to the surface, and the radiation of this pipe and radiation of this pipe. Those are the four factors that go into determining what happens at point Z here. This is a entranceway radiation calculator. I'm going to have this up on the website so anybody can actually use it. But here's just an example. And this is not based on the same radiation tables as overhead shielding. This is based on an air burst. And it's a 500 kiloton air burst. So for a shelter in the 1 to 20 psi range, if that vertical distance is 10 feet, the horizontal distance is 8, and the shelter entranceway is 3 feet in diameter, you're going to end up with about 2.2 REMS in here, based on 12,000 REMS of fallout initial here and 9,000 REMS of neutron. Just notice what happens when you get over here to the 100 psi range. You end up with 108 REMS inside the shelter, which means people would be getting sick. In the POP book, there are established tables for a 30-inch diameter tube. So you can pick the vertical depth down 12 feet, horizontal depth over 8 feet is 1. Now that's for a 30-inch diameter entranceway. If you make it a walk-in entranceway, these numbers go way up, 8, 10, 20-fold. But this is there. You can see here, we've got one entranceway here, there's another one here, and there's radiation bends in these tubes. And that's important especially for overhead entranceway radiation. So in the analysis, you need all the penetrations in the shelter with a radiation bend in it. Dr. Chilton is the expert in the world for entranceway radiation transport through entranceways, and this is the formula that he used. This is in the book. I don't expect you guys to use this. There's a radiation entranceway calculator that I'm going to put on the website, and in the book there are different tables, so you can just look it up. But the total REMS in the shelter, what's coming in from all sources, gamma and neutron, is the distance from ground zero, the size and type of the weapon, the overhead doses from gamma and neutron, and the radiation inside the shelter. And that gives you a total REMS in shelter. So a total REMS in shelter of 14-5 means in the shelter from all sources, you're going to have 14 REMS at 5 psi. 5 psi is a certain distance from ground zero from a 100 kiloton weapon.